their code actually went backwards, counting down instead of counting up. You know, all of our loops have gone 0, 1, 2, 3 up to the length of the array. Instead, they counted down from the end of the array going back. So if you had like a quantity of, let's say, 10, right? Looking at our little chart, a quantity of 10 should get you a 10% discount. Well, how did that happen? What their loop did is it started here. And it said, is there quantity greater than this number? Well, 10 is not greater than 26, so they didn't get the 20% discount. So then it subtracted 1 from I. Is the quantity greater than or equal to that? Well, we're looking for 10. So nope, 13 to 25 doesn't qualify. So they subtracted 1 from I. Is your quantity greater than or equal to 9? Yeah, it is. So 10%. That's our discount, and then you should break out of the loop. So one more thing I want to do is the idea of parallel arrays, which we've talked about quite a bit, but we're going to do one more application of them. And let me kind of type up what I want it to do, not the code itself. But I want it to say something like this. Monday, I worked 6 hours. Tuesday, I worked 8 hours. Wednesday, I worked 4 hours. Thursday, I worked, nothing. Friday, I worked 5 hours. Saturday, I got the day off. Sunday, I got the day off. Right? And so then it could calculate the total based on that information. Whatever that is. 23. It could also print this, right? I mean, this is kind of the way that our data works in our heads, but it could print it out. It could even print out how much you earned each day based on what your salary rate is, right? If you earn, $10 an hour, it would print out a table that looks something like this. I earned 60 that day. I earned 80 that day. I earned 40 that day. Didn't earn a thing that day. $50 that day. Nothing that day, nothing that day, right? So this is a table, and hopefully based on our previous lectures, you can get the idea that these are parallel arrays. We have an array of days and an array of hours worked. Something like this, right? That's days and hours worked. So we're going to write a program that supports that. Now in the past we've been kind of pre-declaring our array, right? We would just write an array declaration and we would stick the values Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday in it. And by the way, I think I'm just going to shorten this to Monday through Friday because as we keep running this program over and over and having to type in data, easier to type in 5 pieces of data rather than 7, saves us a little bit. And then the second one, we're not going to allocate the same way, right? Because the first one we could do something like this. Days is equal to, and then we could fill in the blanks, right? Monday, or if you like lowercase, great. Tuesday, Wednesday, etc., right? But for the hours worked, we're not going to fill in these values, 6840500. Instead, we're going to ask the user for those values. So we're going to need an empty array, an array full of 0 elements. But it's got to be the same length as the days array. And I'm going to be typing this stuff in our real code in just a minute. Right, so to be a parallel array, it has to be of the same length, right? So we could create an array in Python like this. We could just say, okay, I know that I'm going to need room for 5 numbers. Right, that works. That's kind of lame. What if this was 1,000 elements long? What if it was 365 because you were tracking every day of the year? You wouldn't want to have to type in 365 zeros separated by commas. The better way to handle that is to do something like this. I need 5 elements and square braces. They all need to be filled with zeros. That's how you do it in this language. There are other ways in other languages. So these two things do the same thing. But instead of 5, we would probably want to use the length of the days array, right? You don't want just a magic number 5 appearing. So instead it would be something like the length of days. Not that's. That many elements. The book would even recommend that we declare a constant, or we declare a variable that contains the length of the array. But we could always just use the length of that array itself. So that's the idea. We're going to allocate, we're going to declare two arrays, and then we're going to loop our counter for I equals 0 to the length of days. And we're going to print how many hours did you work on, and then we're going to print out that value at that specific days. Days subscript I, right? So it'll print out Monday. How many hours did you work on Monday? When I is equal to 0. When I is equal to 1. How many hours did you work on Tuesday? When I is equal to 2. Wednesday. When I is equal to 3. It'll print out how many hours did you work on Thursday, and so on. And then we have to get our input. H hour is equal to input, get H hour, get whatever we wanted to call it. We have to convert it to a number, and then we can put it into our array. Hours subscript I is equal to that, right? So that's the loop that we're going to write. Then we can print our information out as a table. With a loop. And we've done that so many times, I'm not sure I need to pseudocode it. But for I equals 0 to length of days, which is just the same way as writing, for I in range len days, right? Some variation of that syntax. I'm just kind of doing pseudocode there. And then we would print out the days at that subscript, at that index, and then the hours worked at that position. So at that point, we will be generating a table that looks like that. And that's what we want. So let's get to that. Let's get to idle. April 25. So name, date, parallel arrays with data entry. Keep track of hours worked each weekday. All right, so the first thing we had was our declarations. Let's make our days array. Days is equal to Monday, Tuesday, Wednesday, Thursday, Friday. And I would do the whole month, but the last time I taught this, it got really tiresome typing in this data over and over. And so, at least we're skipping Saturday and Sunday each time, so a little bit of savings. And then so our number of days is equal to the length of the days array. Now we need to allocate our hours worked each day. Hours is equal to the num underscore days times, and this is square braces, not parentheses, the value 0. If we wanted to fill our array up with ones, we would put a 1 there instead. If we wanted to fill our array with the word Bob, we would put the word Bob there. Alrighty, before we go any further, let's make sure that we can at least print the array out. Right, what we're going to do, what we're going to wind up doing is, inserting code above this and pushing it down and stuff like that, because it's not the first thing we really want to do is to print a bunch of zeros. But we would like to make sure it works. So for I in range, we could do either num_days or the length of the days array. Doesn't matter which, because at this point they're the same. Num_days, print days subscript I, comma, hours subscript I. And let's print a little header for our table. Print day, or quote day, space, space, and then hours worked. That might work. And then underneath that, print dash, 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 space, space, and then a bunch of dashes. Alright. Okay, that doesn't look real good. I need to move the hours worked back a column, right? Or to move this one forward a column, but pretty close to working. I'm going to remove a space there, remove a space there, and then when I run it, it'll look pretty good. Maybe we'd like to space it over more, but we can mess with formatting at some other point. That's not the point of the assignment, is the formatting. Okay, so we have the way to print our table out. I'm just going to put a comment there. Why am I calling it a table? Because it's a parallel array, just like a spreadsheet. You got multiple columns where the items are related by their index number. But we need to ask the user how many hours they worked on Monday, how many hours they worked on Tuesday, and so on. That's also going to be a loop. I mean, right, you could do something dumb like this. Don't type this. Print, how many hours did you work on Monday? Like I said, please don't type this. I is equal to input, convert it to an int, and then store it into hours at subscript 0. And then copy and paste that, right, over and over and over. Okay, 1, 2, 3, 4, right. So that would be hours 1 because it was the second day. That would be hours 2 because it was the third day. That would be hours 3. That would be hours 4. We need to change our words here. Tuesday, Wednesday. You can see that this is dumb compared to what we're going to do. Right? Thursday, Friday. Does this work? Sure, it does work. But it's dumb. That's the kind of thing that when you see it, you immediately think loop. Because, we've got this counter that's increasing. So I'm going to delete all that, and then we're going to do it the good way. Again, we're going to need a for loop. For I in range, parentheses, num_days, into parentheses, colon. Let's ask the user how many hours they worked for that day. Print, how many hours did you work on, end parentheses, comma, days, subscript I. Now we need to get our input, convert it into a number, and store it into the array. So, HR for hours is equal to input. Convert it to a float. HR is equal to float HR. And then let's put it into the array. Hours subscript I is equal to HR. I think we better put a comment about here. Use loop to ask the user for hours worked each day. work 10 hours Monday, 20 on Tuesday, 2 on Wednesday, 3 on Thursday, 4 on Friday, and it prints out my cute little table. Bless you. But not during the lectures. All right, so we have an input loop here. How many days did you work on? We could write code that would calculate the total number of hours. Then we could calculate the average number of hours. We could calculate what they earned. That kind of stuff. We may as well do at least one of those things, the total number of hours and then what they earned. So let's do that. How do you get a total? You just declare an accumulator variable and then you rip through the loop with a for loop, adding all the elements together. So we need a accumulator variable, total. Total is equal to 0. And then let's use that other syntax, the for each syntax. So for V, standing for value, in hours, colon, total equals total plus V. Let's ask them what their pay rate is. Print. What do you earn per hour? Rate is equal to input, and then convert it to a float. Rate is equal to float rate. And so we know the total, we know the rate, we can calculate what they earned. Earned is equal to total times rate. And let's print it out. Print total hours worked, colon, end quote, comma, total. And then print $ earned, end quote, or colon, end quote, comma, earned. Five, 6, 4, 3, 5. All right. What do I earn per hour? I'm earning the big bucks, $11 an hour. There we go. 253. Now, hope that makes sense. Hope it makes sense that parallel arrays are just like columns in a spreadsheet. And we can step through them with for loops, just like this. Each item is related to each other by its index number. Here we wrote something that would ask for a value and then store it into the array. Right? Ask for a value. How many hours did I work on this particular day? Oh, great, you told me, so I'm going to store it into the other array. Hope that makes sense. Hope that makes sense. So we're going to go to the next chapter. So here's the top of our program, and I'll scroll down from top to bottom for the video recording. All right. So Chapter 7, File Handling and Applications. So we will learn about computer files, data hierarchy, performing file operations, control break logic, merging files. We may not focus a long time on some of these topics, but we're going to go through the PowerPoint now. And then what a random access is as opposed to the other kind of files, which is where you're doing linear access from beginning to end. So what is a computer file? It's a collection of data stored on a storage device, like a flash drive, a disk drive, reels of magnetic tape, punch cards back in the old days. And so there are basically two different kinds of files. There are text files that can be read with a text editor. Idle is a text editor. Notepad is a text editor, right? So some files you could open up in one of these and see. But what if you had an MP3 file? Could you open it up in Notepad and look at it? No. It's all binary data, right? Not text data. Could you open up a picture, a JPEG, with Notepad and see it? No, it would look like garbage. No, all you would see is a series of random letters and numbers. So text files can have numbers in them. They can have names in them, salaries, any kind of words, page from a book, which can be read by a text editor, like Notepad or Idle. Binary files, things like images and music, not encoded as text. So every computer file has what? A file name. And anymore, computer files also have an extension. And what do I mean by that? Well, it's not necessary for a file to have an extension. It'll work without it. And for the longest time, Macs didn't encourage people to use file extensions. But what the extension is used for is to tell the computer what kind of file it is. If it's a TXT file, it knows to open it with one kind of application. So if I go into my notes here and I find a TXT file and I double click it, it's going to launch Notepad. But actually it's going to launch something else because I reconfigured what I want TXT files to be opened by. So every TXT file that I try to open is going to open it in that application. Now how did I set that application? Well, on a Mac you click on it and you choose get info, something like that, and you can change what file opens it. On a PC, Macs are PCs. On Windows, you can right click on it, do open with, and say choose default program. And if you want all of your text files to open in TextPad rather than Notepad, that's cool. You can pick that. Or WordPad or whatever. So you can change which file extension corresponds to which application. Now, if you're not seeing these extensions, it's because they've been disabled in your preferences, which is kind of a drag. Yeah, you can come over here and see that it says it's a text document or this or that or the other, but the extension is a really useful thing that I wish that Microsoft didn't hide by default. So if you wanted to change it so you can see your extensions, and I'm pretty sure that we've already done this, you choose Organize, Properties, and if you're not using Windows 7, if you're using Windows 8 or Windows 10, it's somewhere else. But anyways, you get to the Properties panel, and I botched it. I need View Options. Organize, Folder, and Search Options. That's what I need. And then under View, I can say, where it says Hide Extensions for Known File Types, you don't want that selected. You don't want it to hide extensions. But if I did click that, then all the file extensions would go away. But that's still how the operating system keeps track that PowerPoint, PPTX files are supposed to be opened by PowerPoint and DOCX files are supposed to be. Now, if you try to upload a file to D2L and it doesn't have a file extension whatsoever, it'll give you an error message and say that's an illegal file or something like that, which will vex the Mac users who are creating files with no extensions, because you don't have to create file extensions on a Mac. But then you just have to go and add the file extension, do a save as or whatever to give it the file extension that you need, and you'll be able to upload into D2L. And by this point, I'm sure that the Mac users have already figured that out. So how did Macs get away with not having file extensions? They had a separate table that was stored in the computer's hard drive. that said, oh, this file, by the way, is linked to this application, and this file is linked to this application. But they kind of got away from that, so they use file extensions now too, just like Windows. So it has a file name, January payroll, previous month sales, and it has an extension, txt, meaning it can be opened in a text editor. .dat, it's a data file, but we don't really know what kind. .docx, that's a Word document. So computer files also have a creation time and a modification date. You ought to be able to go and find a file and right-click on it and do properties or get info or something like that, and then you'll see when the file was created. Well, that one was created on Monday, February 19. When it was modified, well, it was modified that day. And when it was accessed. Well, I'm going to open it and see if that access date time changes. All right, so I've opened it now. So I'm going to close it, right-click, do properties again. It still shows that it was accessed on February 19, so I'm not sure what it's going by there. But we see that the file has a name. It's got a location on the disk, on the hard drive. It's got that directory path. It's got a size, 104 bytes. It's a text file, so it's 104 characters long. If we opened it up and we counted it out, it'd be about 104, but you'd have to include hitting enter as part of the count. 1, 2, 3, 4, 5, 6, and then enter 7, 8, 9, 10, 11, 12, 13. 14, 15, 16, 17, 18, something like that, and that would add up to 114. So the file size is measured in bytes. A byte is 8 bits. It's 1 character of text. A kilobyte is 1,000 bytes, more or less. It's actually equal to 1024. Now, chemists and physicists disagree with computer scientists about the definition of kilo and megas and gigas and stuff like that. You know, like if you have a kilo of drugs or whatever, it doesn't mean you have 24 grams of it. It means you have 1,000. You know, and mega means 1,000,000 to the physicists and chemists, and giga means 1,000,000,000. But in computer terms, a kilobyte is 1024 bytes, whereas a megabyte is 1024 kilobytes, which is about 1,000,000 bytes. And a gigabyte is 1024 megabytes, which is about a billion bytes. And you may have bought a terabyte drive for your home, you know, your home system or whatever. That's 1,024 gigabytes, which is about 1,000,000,000,000 bytes. Kilo, mega, giga, and tera just being Greek prefixes, right? Kilo being 10 to the power of 3 in physics and chemistry. Mega meaning 10 to the power of 6. Giga meaning 10 to the power of 9. And tera meaning 10 to the power of 12. And why is it 1024 rather than 1,000? Well, that's just because of the way that binary works. If you're counting up numbers and you keep doubling them each time, where's Notepad? You know, you have 2, 4, 8, 16, 32, 64, 128, 256, 512, and then 1024, right? So you can access that number with 1 bit, right? 1 bit is either a on or off, so it has 2 possible values. If you have 2 bits, you have 4 different possible values, right? You have all the variations, 0, 0, 0, 1, 1, 0, and 1, 1. I'm going to stop doing that counting off after 3 bits. So 3 bits get you 8 different values, right? 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and then all the same ones with the first one changed to 1. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? And that's where I'm going to stop for obvious reasons. 4 bits can get you up to 16 different values. 5 bits can get you up to 32 different values. 6 bits can get you up to 64 different values. 7 bits, right, can get you 128 different possible values. 8, which is a byte, can be up to 256 values. So if you were encoding the English language, you know, you had 26 uppercase letters, you had 26 lowercase letters, you add those together and that's 52. And then you had 10 numbers, 10 digits, so that would be 62. And then you had a handful of punctuation, you know, parentheses and commas and stuff like that. So let's say that that's like up to 72 different possible characters you need. 72 different buttons on the keyboard or whatever, you know, including the shifted versions of that. How many bits would it take to store one character from your keyboard? Well, 6 bits isn't enough because when we were adding up all of our letters and numbers and stuff like that, we came up with more than 64. 7 works. So the original version of ASCII that was defined was for 7 bits. And then that left all the numbers between 128 up to 255 free for computer manufacturers to determine themselves. And so you wind up with interesting things like, you know, how am I typing this? I'm holding the Alt key down and I'm typing in 3 digits and I'm letting it up. Right, so 156, hold the Alt key down, 158, let it up, 159, 160. So this is part of the extended ASCII character set. The basic ASCII character set is the 7 bits. That's all the characters on the keyboard. And then there are other ones. And then they go out even further, like there's a smiley face somewhere in here. I can't remember what it is. Obviously, I'm not going to find it. Is 256 enough characters to hold every letter in the world? No, right? Because once you, you know, add up all the Japanese symbols, the kana, the kanji, or whatever, and then you know, the Hindustani symbols and Swahili and all the Russian letters and, you know, Greek and stuff like that, you wind up with way more than 256 different possibilities. So, modern languages, modern computers have something called Unicode as well as ASCII. ASCII is used for plain text, but Unicode is used in something like Word documents and stuff like that, where people are going to be needing to type in, you know, those various languages. And when things are downloaded from the computer, from the internet, they are stored in Unicode. Unicode just means that you have more space. It's a 16-bit character set. 16 bits meaning that you have way more different possible letters to play with, right? And so they have put in German and Russian and stuff like that. So anyways, that's 9 bits there, getting up to 512, and then 10 bits get you up to 1024. I'm going to count a little bit higher. 2048, 4096. My brain breaks at that point, so I'm just going to say 80, 200, and then 16, 400. I know that's not right. And so that's 11 bits, right? 12, 13, 14. So I do have that one memorized. 32768 is 15. And then 64, 65535 is 16 bits. So your old Sega Genesis could display, you know, pick from a color palette of 65,000 different colors. Whereas your old Nintendo, the 8-bit one, could pick only from a palette of 256 colors. So the graphics are cruder, right? And also the number of pixels on your screen would be determined by the number of bits, you know, that were allocated to the video memory. And if you had something that was only, you know, 128 pixels wide, you know, something like that, like an old Atari or something like that, its information would be stored in much fewer bits than, you know, our modern computers that have, you know, resolutions of 3,000 by 2,000 or whatever.
What about 2?
Pardon me?
What about 2? That ain't gonna be nothing, 1 bit.
Yeah, so that's 1 byte, and so this is actually 2 bytes. And so your Super Nintendo and your Genesis were 16-bit machines, and I think the PlayStation's jumped up to 64 bits, at least 32. And, you know, if you pay attention to Windows and what version of software you're installing, you'll hear people say, okay, Are you going to install the 32-bit version of the software or the 64-bit version of the software? The only difference between those two primarily is how much memory they can access. So there's a formula from going from this to this, that number to that number, how many bits and how many, different combinations. And it's 2 to the power of n. So 2 to the power of 1 is in fact 2. 2 to the power of 2 is in fact 4. 2 to the power of 16 is that. So what if we had a 32-bit operating system? That would be 2 to the power of 32 different bytes that it could address. Let's figure out what that is. 2 to the power of 32. Well, that's a large number. Is that gigabytes? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so if you have 32, you can address about 4 billion bytes of 4 billion bytes. But, right, your desktop computers now come with more than 4 gigabytes. Gaming machines may have 16 or 30. I don't know what y'all kids are playing with anymore. So that's why you had the 64-bit operating systems invention. 2 to the power of 64 is just a dramatic, incredible number. 2 to the power of 64. There we go. That's huge, right? It's 1.8 followed by 18 zeros. So 1, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Right. I don't think that our computers are going to need more than that, more than a 64-bit operating system real soon. So if that's that many bytes, how many kilobytes is it? Well, it's that many kilobytes. How many megabytes is it? Well, I'm going to take 3 more off, and it's that many megabytes. Well, how many gigabytes is it? Okay, gigabytes. We're still a long way from figuring it out, but right, how many terabytes is it? It's 180,000 terabytes. It'll be a while before you install a computer on, on your desktop that has that many gigabytes of RAM in it, or even a hard drive that's that large. So 64-bit operating systems are adequate for now. So 3 files showing their names, dates of modification, types, and sizes. There's the file name, but they disabled extensions, like you can read this because it's blurry. That was the date it was modified. That's the type of the file based on the extension and its size. Now when you're looking at your folder, it's different on Macs, but the same concept. You can pick how you want to see your data, right? If I'm looking at it like this, they're great big icons. But what if I want it in a cute little list that shows the file sizes and stuff like that? There's a little pull-down menu here that I can pick, okay, I want to see all details. And you go, well, that's not very many details. If you come up here and right-click on this header bar, you can pick more details that you want to see. Who's the owner of that file? Alrighty, system, the administrators. I own some of these files. I'm going to enable another header. So I'm going to right click on one of these header things and file description. Looks like all the file descriptions are blank. There's even one called more. There's all sorts of interesting things. Album, album ID, anniversary, assistant's name. Now that's really crazy to be able to have that information in here. City, copyright. Okay. It's very unlikely that you're going to be able to get much of that information. But if you were looking at a folder of pictures, then you might see things, you might be able to choose extra headers that would show you information about your photographs. Or if you're looking at a folder full of MP3 files, then things like album and album artist would be of interest. So those are all attributes of the file that is stored by the operating system, so that it knows that, that this MP3 file, the artist was named Prince, right, and the album was Purple Rain or whatever. Wrong. So, organizing files, directories, and folders. A long time ago, if you put a floppy in, all you could do was just have one list of files in it, right? You couldn't create folders on it. But, that was kind of lame. So people made the ability to create folders on your floppies. That's how the files are organized, right? Now, I'm not going to even get into that. Of course, there's not really folders on your disk drive. It's just organized electronically because there's a table that says that this file is stored in this folder and this file is stored in this folder. So what is the path? The path describes where the file is stored. This is what's known as a fully qualified path because it's got everything. It's got the drive letter, and it's got all of the directories, all the folders, and then it's got the file name and extension. So that's the drive. These are the folders, and that's the file name and the extension. So if I open up a file and I right click and I show properties, I will see that stuff. Not that you can see what I'm looking at, but you've done this before, I bet. You go into the properties and you can see that this file is in this directory. C, program, files, JetBrains, PyCharm, all that kind of stuff. Right there. So that file is stored in C users public desktop. Again, it's different if you're using a Linux file viewer or the Mac Finder or whatever. So a data hierarchy describes the relationships between the data components. Characters, fields, records, files, and databases. Right? A database can hold a bunch of files. A file can hold a bunch of records. A record can have a bunch of fields. And a field contains a bunch of characters. And what does that mean? So like you might have something that's supposed to represent patient data. And so you have a first name, you have a last name, you have a date of birth, and then you have their address or whatever. Each one of these would be fields. Each one of them, would be composed of characters. Jeff Dobson, database, birth, whatever, 1180s, whatever. And then my address is, 123 South Main, whatever. So each record is composed of 4 fields. A database, a file, could have hundreds of records. Or thousands, right? Or millions, billions. And then the database could have multiple files, tens, hundreds of files. So this record has 4 fields. Each field has a certain number of characters. So that's the data hierarchy, right? Database the largest, file, a record, and then a field. So we have several records in our file here. Henrietta Smith, got that number, that year of birth, and some whatever this YY, and then the state that they're living in, it looks like. So Denise Mitchell, this is one record. The field Denise is composed of several characters. So a record has a bunch of fields, a field has a bunch of characters, and then a file contains a bunch of records. So file operations to use data files in your programs. You could declare a file identifier. And then you open the file. And then you could read from it. Input the file, output the file, that kind of thing. So reading from a file and processing the data, every programming language has a different way of doing it. In many languages, a delimiter, such as a comma, is stored between each data field. So if you open up some files, you'll see data stored like this. My name was Jeff, comma, Thompson, comma, and I was born in, 1/1/76, comma, and then my address is 123 South Main. Now, is comma a great delimiter? Not really, because people like commas, right, in their names or in their addresses or something like that. So other programs will use tabs, right? They'll just tab them apart like that. But the tab is actually the slash key character, something like that. And so some people put quotes around each piece of data and then separate them by tabs to make it really easy for the program to decipher, what it's reading, what it's seeing. Anyways, the delimiter is a symbol that separates the items. So Jeff, comma, Thompson, comma, 1/1/76, comma is my delimiter. I would like to modify our little program to save its output as a file. So I'm going to fly off the PowerPoint for a little bit. We're going to need a file name. Let's ask the user for a file name to store in. File name is equal to input save to what file name, question mark, space, end quote, parentheses. All right, I better Google this up before I make any huge mistakes, waste too much of our time. All right. So now we need a file. I'm just going to call it the word file. File is equal to open. I'm going to open that file name. So open parentheses file name, comma, quote, W for write. If I was going to read, I would put quote W read. And again, this differs on what programming language and environment you're in, but the concepts are the same. So we have a file. Now let's write to it. So, file.write payroll report. But then put a \n at the end of that. Backslash meaning the one that's above the enter key, not underneath the question mark. And now we need a loop that's going to go through and print out, the day, the hours worked, maybe the amount that they earned that day. So, file.write, wait, we need a for loop. For I in range, parentheses, num underscore days. Let's write out the days, subscript I. Let's write out a comma, so quote, comma, quote. Let's write out the hours. So hours, subscript I. And let's write out another comma. Right parentheses, quote, comma, quote. And then let's write out the hours times their payroll rate. So write hours, subscript I, times, that's a star, not a plus, rate. And then we're going to write a /n to go to the next line of the file. We didn't have to do that on print statements in this language. We didn't have to use /n's, but we could have if we want to insert blank lines. But files do not assume that you're going to the next line after every write. It's not like a print. So when we wanted to go to the next line, we wanted to hit enter on our keyboard, had to do the /n. And then let's close our file. File.close. If you don't close the file, the operating system keeps it open as long as your program is running. And if the file is open, then you won't be able to like grab it and move it to another directory, right? If you needed to. So in general, your programs want to close the file as soon as they are done using it, rather than just hang out and leaving it open. If it's open, it may not be able to be backed up, uploaded somewhere. Alrighty, I hope this works. I'm going to test mine real fast. Make sure that I don't have any syntax errors. Alrighty, write is not supported. Okay, so I've goofed. It should have been file.write. You see every one of these writes I did? Change them to file.write. The easiest thing to do would be to just do a copy and then some pasting. Every one of my writes needs to be file.write. My mistake. And I'm still getting an error. Argument must be a string, not a float. Okay then. This is getting annoying. We're going to have to make a couple of more changes to 3 of our write statements to get this to work. You know how when you do math, you have to convert it to a number? Well, when we want to write it to a text file, we have to convert it to a string. So you see, after each one of these parentheses on these write statements, we need to add this, str parentheses. But only do that, don't do that for the ones that are printing out the commas or the \n's. Just do that for the ones that are printing out days. Excuse me, numeric values. So on the line that said print days, print str parentheses days. And you're going to need 2 closing parentheses at the end of that file, at the end of that line. We need to do the same thing to the hours line. File.write parentheses, str parentheses, hours, and then 2 closing parentheses. And then do that for that last one, hours times rate as well. File.write parentheses, str parentheses, and all of that stuff ending with 2 closing parentheses. Alright, it would have been nice if I had put out a message saying that file was written successfully or something like that. If you get your code working, if it'll run without error, run it and then give it a file name like pay.txt, something with a .txt extension, and then go to your scripts directory and you can open your report. And this will be the last thing we do today. So, how many hours did I work on Monday? Well, I worked 5 hours Monday, 6 on Tuesday, 7 on Wednesday, 8 on Thursday, and 9 on Friday. Whatever. How much do I earn per hour? I earn $10.95. Save to what file name? Pay, P-A-Y, .txt. Now that I've done that, if I go to that folder where my script is located, I'll see a pay.txt file. And if I double click on it, there's my report. There's my payroll report. This is a comma delimited file. Now, strictly speaking, we probably wouldn't have that first line of text in there, right? That's the kind of thing that a human wants to see, but a computer doesn't want to see that. So we probably would not have printed that. All right, so I'm going to bring the code back up, and then I'm going to describe the homework. If you have any extra typing to do, and what is the homework going to be? Well, you know, in this one we inputted hours per day. The homework assignment is you're going to have a list of months, and you're going to input the high temperature for that month, right? High temperature for January, question mark, and you're going to type in 12. It was a cold January. High temperature for February, it was 34. High temperature for March, 45. High temperature for April, right? And so you're going to go through and you're going to enter, temperatures. You're going to enter 12 temperatures, and then it's going to print out a table. Doesn't have to calculate the total temperature and the average temperature and, multiply by K rates or anything like that. That's just what it is. So you're going to have an array of months, and then you're going to have an empty array of temperatures, and your input loop is going to fill in that empty array. Just like this one had a table full of days and a table full of hours. Right? It had a table full of days, and then we had a table full of hours, and our loop filled in the hours array. So your homework is going to have a table full of months and a table full of temperatures, and your loop is going to fill in the temperature array. Then you're going to have another loop that prints it out. So basically your code is going to look like this part of our in-class assignment, from there down to there. You're not going to need anything else other than that. Alrighty. Let me make a Dropbox for the folks who did get this to work, but then I need to wander around and make sure that y'all have it going on. Alright guys, if you refresh your assignments Dropbox, you should see Dropbox S parallel arrays and writing to a file. So that's where you'll want to upload it.